Going to be shorter. This is part 2 of notes for 9.1, 9.2. So we're starting off with tetrahedral electron domain. Take a look at the tetrahedral. I'm going to repeat myself just a little bit here. So we start off, notice that if I have 4 electron domains, I have this shape called tetrahedral, and if each one of those is a bond to an atom from the central atom, in other words, I have 4 bonds around my 4 B's connected to my A, then the name of the electron domain, there we go, which is tetrahedral, is the same as the shape of the molecular geometry when all 4 are bonds. If we have one, excuse me, if we have one that is non-bonding but 3 bonds, it keeps the same shape because of the lone pair at the top. Here's what I mean by that. The lone pair at the top here keeps pushing off on the electrons in the bonds, so we keep the same shape except you don't see the top part. It's like the top part is gone, and then what we have then is just trigonal pyramidal. So it's a very shallow pyramid. You can see the A and the B's for those 3 form this like 3-sided low pyramid. And then if we take away 2, just like we do for H2O, notice that I have the lone pair and nothing here, nothing there. So all we have is that is like a bond angle like that, which is why we always draw water like this. You always see it like this and never like that, because that doesn't account for the lone pair that we see there and there. Okay. So just going over just quickly through some shapes that you're going to see a lot of. Tetrahedral is the most common one because of carbon. So we start off like carbon. This is methane with CH4, and this is what it looks like 2-dimensionally, but 3-dimensionally it looks like this, and that makes a huge difference. And carbon makes lots of bonds, so we're going to see carbon an awful lot. This is one step up when you have an expanded octet. Something like phosphorus can do this pretty well. Remember when I said we have something like PF5 and I drew something that looks like this? This would be back in chapter 8. So I put 5 bonds around phosphorus. This would be the trigonal bipyramidal. So trigonal bipyramidal has this extra thing that's important. So as it turns out, the ones that are along the middle, the bonds going around the middle of trigonal bipyramidal shape, are called equatorial bonds, like you go around the middle of the Earth for the equator. And then the ones that are on either side, like top and bottom, would be axial bonds. Now the difference between these is the equatorial bonds have 120 degrees between each equatorial bond. I know it doesn't look like it because of the 3-dimensional drawing, but the axial bonds have 180 degrees between the axial bonds. But the axial bond compared to the equatorial bond is 90 degrees. So this actually has 3 degrees. It has 90 degrees from equatorial to axial. It has 120 in between equatorial bonds, and it has 180 in between axial bonds. Okay, so this is one of those things where, like, we got to remember all 3 of these. We usually, like for tetrahedral, we just have to remember 109.5 for the most part. But the rest of the shapes only have 1 degree, but this one is specific because the bonds going around the middle are different than the bonds going from end to end or top to bottom. Okay, so please make a note of that difference between axial bonds and equatorial bonds. When we take away bonds, we always take away an equatorial bond. So here is when we have 4 bonds, we have the trigonal bipyramidal shape, but we take away one of the bonds, which means that we take away an equatorial bond, and we end up with something like that. Some people call it hot dog, like when you hold a hot dog bun with hot dog in the middle, because they think it looks like that. Some people call it taco. I forget exactly what the actual shape is called here. I'm sure it says it here. Seesaw, they call it seesaw. And if you were in class, I would show you what the shape looks like and show you why they call it seesaw. Seesaw because it goes like this, and you can go back and forth. This can go up and down like that, and that's why it's called seesaw. If we take 2 bonds away and have non-bonding pairs there, then that's called T-shape because of this shape like that. and if we take away 3, then it's just linear because the axial bonds remain. Okay, the last one then would be octahedral electron, which we also call hexahedral. So for this shape here, if we take 1 away, it doesn't matter which one we take away, we end up with something called square pyramidal. So that means that we have a pyramid that has a base of a square like that. I know you can't see the drawings and it doesn't really matter, but you get the idea. If we take away 2, then we end up with square planar. So we always take away 1 on one side, 1 on the other side, so we're left with 4 all on the same plane, which is where we get square planar from. Okay, moving on to large molecules. So when we talk about bond angles, or we're talking about the molecular geometry, we have to consider what the Lewis structure looks like. So for the first carbon here, there's 3 carbons, well there's 2 carbons, but there's other things here. Like this is an end, so we don't consider this one to be anything, but we do have geometry for that oxygen because it's combined with 2 things. So the first carbon there has 1, 2, 3, 4 bonds, so that would be tetrahedral. The second carbon has a double bond, but it's only bonded to 3 things, which means it's trigonal planar. This is how we tell what the molecular geometry of each central atom is. And then the last one, now this one kind of freaks people out, but this is tetrahedral also, and here's why. This oxygen has 1, 2, and then 3, 4 electron domains, and because it's 4 electron domains, it's tetrahedral. Now the actual shape, molecular shape of this though, would be bent because there's 2 lone pairs. Okay, so that's how we tell the geometry of, there is no like geometry of the whole molecule. We don't talk about that. What we talk about is the geometry of each of the central atoms that we're looking at. So you can take a look at here. You can see here again is tetrahedral. Here is trigonal planar. There you can see the 120 degrees in between this, and then here you can see it's bent. Okay, so this is the same molecule that we had on the last page. Okay, and that's it. I told you it was going to be shorter. That wasn't very long. Stay tuned for notes for 9.3, 9.4.